This podcast is brought to you by LMU Munich.
Okay, good morning. So the joke. So we'll continue with this discussion that we had. So let me just remind you what was the story. So we discussed briefly all these mysterious properties that black holes have. Okay, so there was a list of the properties, and then we asked the question what to do. Okay, with this. I mean, there are several options. Of course, there is always an option to postulate that quantum gravity does something unusual, in the sense that it violates whatever, energy conservation, CPT, all this exotica. Now, there are two reasons why I don't want to take that road, because there are excellent arguments that say that if quantum gravity does anything like that, if this is the explanation of black hole physics, this exotica, this quantum gravity should do it at large distances, because black holes are macroscopic objects. And there are excellent arguments. I don't want to enter in this discussion, but there are excellent effective field theory arguments that you can see immediately that then it would be extremely hard, if not impossible, to get away with observing nature, okay, at low energies as we see it, okay? So this tells you that there is no free lunch. You cannot take quantum gravity and blame on it all possible exotic phenomena without paying the price to why you don't observe those exotica in everyday life, and not just observe. I mean, everything would become different in effective quantum field theory. So therefore, I am not going to take that road, that quantum gravity violates unitarity or CPT or causality or anything like that, okay? Because I think that road goes to nowhere. But okay, it's a legitimate question, of course, to ask. So instead, I will try to ask the question that whether, I mean, there are other approaches, of course. We don't have to necessarily violate CPT and stuff. We can try to study things directly in the theory of quantum gravity. It's a fully legitimate approach. Or try to use power of theories of quantum gravity. For instance, in string theory, try to use power of supersymmetry and BPS properties. And this has been done by Strominger, Baffa, and these people, to understand the origin of entropy, etc. So, or use power of ADS-CFT to try to understand. So that's a full legitimate road. That doesn't require a violation of unitarity and exotica like that. But the approach that I took in these lectures was even more modest. So what I'm asking is, let's try to come up with a microscopic model, okay, with the only requirement that this is also a model of enhanced memory capacity. Okay, so this is one thing I'm asking from this theory. And then let's see, once this theory realizes this property, enhanced memory capacity, whether it also has some other features that we observe in black holes. Okay, so this is the question. If we don't, then this will be informative. Okay, if we observe these other features, then we can ask whether this is a coincidence or there is some fundamental connection. Okay, and also the power of this approach is that I'm not necessarily asking a specific model. The only thing I'm asking from the theory is that it has this property of enhanced memory capacity. Okay, and so we wrote a model the other day. So there is a class of models. I just took one representative because you can play around with these models and you can see the by changing parameters and type of interactions, etc. These key properties remain. They are robust. So we wrote a model, right, that was based on a simple non-relativistic Hamiltonian. Basically, the picture was described. So we were describing a d-dimensional sphere, okay, and a bosonic particles, a field describing fluctuations of occupation number of bosonic particles on a sphere. Then there were, so the only thing that we imported from gravity was momentum-dependent attractive interaction. So I want to have at least some regime. I'm not asking that this is a dominant interaction in all the regimes, but I want to have at least some regime where this interaction is important. Okay. So this is the point. So this sphere has a volume, which again I call omega. So I'm normalizing this with the volume. So this was the sector, and so we showed that this sector exhibits the following properties. So there is a Hilbert space, okay? And we are interested specifically in the situation when the scale is large. So there is a self-interaction, but this self-interaction, since it's momentum-dependent self-interaction, so it's stronger for high momentum modes, just like gravity, right? So in gravity, this is what we have. And so for high momentum modes, it's stronger. And correspondingly, I'm asking the scale lambda to be sufficiently large, so that I want to go to sufficiently high momenta before theory becomes strongly interacting, just like gravity, right? So in gravity, we have similar situation. We have Planck mass, which for macroscopic for macroscopic theory is small, but for microscopic theory is huge. Planck mass is about mass of whatever, 10 to the minus 4 grams or something, 10 to the minus 5 grams. It's a huge mass, so you have to go all the way there in momenta of gravitons or other particles in order for gravity to become strongly interacting. So it's a similar property here, okay? So high momentum modes are the ones that are experiencing this interaction, okay? For low momentum modes, these interaction terms do not matter. They don't see them. They behave as if they are free, okay? Okay, so now, so in this picture, we ask this following question. Okay, we have this theory, and let's investigate the Hilbert space of this theory, okay? So. And in this Hilbert space, what we discovered, so if I think of it as a Hilbert space, we discovered states, macro states. So macro states means that states with certain macroscopic characteristics, okay, that were holographic. Okay, we didn't impose it, we didn't ask for it. That's a property of the theory. Okay, so these states, so pictorially think in the following way. So this is Hilbert space. And in this Hilbert space, we have states with holographic properties. Now, these states were what is the macro characteristics? The macro characteristics was the occupation number of the soft mode. Okay, so we had a soft mode. Let me call it a master mode. So there is a master mode. so very soft. Okay, let me call it simply soft. And this mode is, in this particular case, A0, okay? So it's a master mode. And so there is an occupation number of this master mode that we call N, okay? Capital N. And so what we notice is that when, for certain discrete values of this occupation number, N, okay, the mode, the state here, delivers a set of gapless modes. Okay, so there is a set of, so this is state A with occupation number of A0, and then the same system delivers now figure N. Okay, let's not confuse it with the story. Okay, so let me call it certain K star for certain values of K star. Certain number of modes that are gapless. Okay, and now the interesting thing was that this number of modes that are gapless, it scales like area of the sphere. Okay, in the units of corresponding momentum. Okay, so this is always scales as area of the sphere. Now, these are, so therefore, so what happens is that when the master mode gets occupied to certain macroscopic level N, it dictates a set of modes to become super soft, okay? And so there is a set of super soft modes, and these are the ones that we call holographic. So, in a sense, what Dieter was asking yesterday, so there is an emergent conformal symmetry, basically, because this is as conformal as you can have in non-relativistic theory. You are all of a sudden delivering a set of gapless modes with interaction that goes to 0, and I take N to infinity, okay? So, and these are modes which are AK star AK. These are their occupation number. And now, their occupation numbers, okay? These occupation numbers, which I denote by small n, okay, for these modes. Now, of course, the K star level is degenerate, right? So in degenerate, we have this number of modes. So therefore, occupation number of these guys, since K star is simply a label of a level, so K star is not a label of individual mode, it's a label of a level. Okay, now individual modes, they have their own labels, okay? And these labels I can call for each K star, I can label for each mode that belongs to, for each K that belongs to K star, I can introduce another label, J, let's say. And so these are modes that belong to J, okay? Now, and these are the modes in which we can store patterns, information, okay? So then we introduce basic vectors, pattern vectors. These are vectors from N1 to N up to nk star, because J runs from 1 to all the way to nk star, figure N, k star. Okay. So again, notations, don't confuse notations. So capital N, once and forever, will be an occupation number of the softest mode, of the master mode. Figure N with index k star, that stands for the number of modes, not the occupation number of each mode, but number of modes. And the occupation number of each mode is I'm denoting with a small n, okay? Then we have this story. So what does this mean? Now, this means that all of them are given by the same characteristics n with small fluctuations. Why small fluctuations? Because this theory is number conserving, okay? So therefore, the theory automatically, whether we want it or not, splits into superselection sectors with a fixed number. Okay, so therefore, what happens here is that there is a neighborhood of the Hilbert space of this mode n. Okay, and this neighborhood is parameterized by the states in which I redistribute a little bit occupation number, not a little bit, I can also distribute it too much. I distribute occupation number from master mode to other modes, okay? So with the total sum of these modes to be equal to n, okay? Now, we restricted ourselves with small excursions, okay? You don't have to restrict yourself with small excursions. You can also consider states in which these individual n's, they go above, they are 10, 100, or whatever, okay? The reason I restricted to the occupation numbers plus or 0 or 1, because considering higher numbers is not increasing terribly the entropy of your information device, because the entropy only scales logarithmically, okay? So entropy increases exponentially with increasing number of modes, that's what counts. But if you increase occupation number of individual modes, that only increases entropy logarithmically, okay? You can do it, all right? So therefore, Nj, in my discussion, I don't have to go beyond that. I can restrict it to 0 and 1. Again, it's up to you. You can study different situations, okay? So therefore, the picture is like this. So we have a macro state, and in this neighborhood of macro state, we have microstates, okay, with the area low entropy, and okay, holographic. Now, then we can change n by a lot, okay? When I change n by a lot, by a certain jump, okay, I can define a different macro state. So, in other words, there are discrete sets of for n, and let me call this n minus delta n, let's say. And these discrete sets, they give another neighborhood, holographic neighborhood, okay? So, and another set of gapless modes emerges here. There is another set of gapless modes, let me call them k star prime, and the story repeats, okay? Again, entropy scales as area in those, in terms of this units and so on, okay? So what do we see is that in the Hilbert space, there are islands of holography, and these islands of holography are separated by terrain that doesn't support any gapless modes, okay? So the gapless modes are supported in the neighborhood, in another neighborhood, and so on, okay? So these are enhanced entropy states, and they are intermediate states that do not have enhanced entropy because they don't have gapless modes, okay? Any questions? Yeah?
The supersoft modes, their typical wavelength is of order R, right?
No, that is the important thing. So here, the story is this, right?
Yeah, okay, if I would think about a black hole, then the super soft modes, their typical wavelength would be of order of the horizon, right?
No, that's the thing. No, that's the point, precisely. So that's the typical mistake that I was making for a long time, okay? I thought that's right. So the point is the following. So the super soft modes are modes that have wavelengths. So in general, right, for a free particle, we have dispersion relation, which relates the wavelength and the frequency, okay, energy and momentum, right? And so for a free particle, obviously we have relation that if they have low energies, the momentum is also small. This means that low frequency particles, they have huge wavelengths, okay? Now, if I give you a particle with a wavelength of order L Planck, okay, for a free graviton with this wavelength, the energy or frequency, of course, will be also M Planck, okay? Right? However, these modes now are precisely analogs of these K stars. Okay, so K star, you can think of K star in this theory as analog of extremely high momentum mode. But this extremely high momentum mode, because of the background with high occupation number of the soft mode, no longer has the same dispersion relation. In other words, what happens in the black hole, that's my idea and our idea, that what happens in the black hole, I don't want to go to black hole, but since Dieter is asking, So what happens in the black hole is that the black hole creates a background, okay, on which there are certain Planck wavelength gravitons that become gapless in frequency. So their wavelength is still Planckian. Okay? So therefore, what happens is that despite the fact that their wavelength is Planckian, meaning that the momentum k star is very large, okay? The number, the wave number is huge, their energy is 0 or very small. This is the point. So, okay, this is the key because this is what we should. So, what black hole does, according to this analogy, anyway, it doesn't matter whether we talk about black holes or not. In this theory, what happens is this: that a particle that, if it would be free, would have a huge energy, but it's not free. It's interacting with huge collective effect of soft quanta, and the energy goes to 0. Okay. So now, this we. Absolutely, you can think of it as a redshift. Very good point. Yes, you can think of it as a redshift of energy. Yeah, in a certain sense. Okay, here of course I don't have gravity or anything like that, but so in other words, right? So the spectrum, right? Let's draw the spectrum, and everything will be clear immediately. So what is the spectrum? So the spectrum of a free particle. So in other words, if I would remove this interaction of modes, right? If I would remove interactions, right? I would simply have a free particles on a sphere. And free particles on a sphere would have dispersion relation, which is linear so this is energy, okay? And this is frequency. Or this is frequency, or not the frequency, but the harmonic number, the momentum, basically, right? So this is momentum. Don't get confused that it's denoted by omega. It's a momentum, right? And so this is omega, and then we have states, right? We said we have states. We have states. Let's say omega star. This is with momentum k star, right? K star. And then here somewhere there is, let me call it omega prime with momentum k star prime. All right. And what is the picture? The picture is this would be a free spectrum. Okay. So this would be a free spectrum in the absence of this. Now, however, because of this interaction, what happens is that the particles with low momentum, they don't see this interaction. Okay? They follow this line, and then they come down, and they go up again. Okay? Right? Because this was dispersion relation that we got from around the states, right? As we said, the Hamiltonian had a form. Hamiltonian had a form of right? This was the form of the Hamiltonian. Now you see the point, right? So you see that if I would not populate the system with occupation number of A zeros, okay, nothing would happen. Spectrum would be just like free. So this is n, right? So this is the spectrum for essentially n equals 0, free spectrum, okay? Right? But now, for the n that is critical, that makes the 0, right? So n that is critical, this n satisfies the relation, right? When this is 0. This means that n satisfies the relation that E over lambda omega k is 1, okay? Whenever you satisfy this, you have a critical level, okay, which is holographic. Now, omega k in general scales as k plus d minus 2, right? So this is just a property of the spherical harmonics, right? Okay, and so therefore this is what is satisfied by the holographic level, right? So holographic level satisfies this relation. We can translate it with, so it's n, occupation number of 0 mod, E over lambda, k plus d minus 2 is 1. Okay, this holographic level. And there are discrete sets of these guys. So now you can ask this question, all right? You can ask this question. Let's say I make some level holographic, k star. So for k star, this is satisfied, okay? So for k star, we are here. And we can ask this question, by how much I have to change n to get to another holographic state, okay? Right? So this is the change that you require in n in order to change k by 1, because k is an integer, right? So you have to change k by 1 with very good accuracy, right? So, and this requires delta n, certain delta n. How does this delta n scale? It's very easy to figure out from this relation, right? So in other words, this means that n plus delta n times this story, E over lambda, certain change, in which I change k star by L, okay, by number L, again should be 1, okay? And from here you can find corresponding delta n, L corresponding to a neighborhood number L, okay? So these are the two k and k stars, k prime that is separated from k star by distance L, all right? And you can figure it out how this scales. It's very simple. Why? Because we know what k star satisfies. So once for n, you satisfy this for k star. We know what it satisfies, okay? And corresponding delta n, you can see it very easily. The scale says, okay, is L times n in power 1 minus 1 divided by 6d minus 2. Okay, so this is the scaling. Okay, these numbers, I don't see any importance in these numbers. They happen, whatever they are, they dimension dependent, okay? But the point is that there is a certain delta n, okay, which depends on the level of the neighborhood, okay? And if you ask how much I should change n to go to a next holographic state, that's the amount you have to change n, okay? As simple as that. Right, so therefore, let's restrict our attention to nearest neighbors, okay? So L is equal to 1. Let me take L is equal to 1 for simplicity. Not simplicity, just nearest neighbors. Okay, so then we see what is happening, right? So I have the state k prime and k star. They differ by 1 step. Then the spectra are different. So this is spectrum for n. This is for n equals 0. In other words, this is spectrum for A0 dagger, A0 being 0. This is n. And then there is another state. Let me see. Okay? So this is n minus delta n. Delta n given by that expression. So from now on, whenever I say delta n, this is a strict variation of n, which takes me to a nearest holographic state. Generic variation of n, I will denote by variation of n. Okay. So delta n means strictly 1 step. Okay. Now.
It changes the macro state, not the micro state, so to say.
Yeah, it changes. It changes both. It changes macro state, and therefore it changes everything. Right. That's right.
So it goes from one black hole to the other one.
Exactly. It goes like, yeah. If you want to map this to a black hole again, Dieter is eager to map this on a black hole. Right. To get a video, absolutely. No, thanks very much. Yeah, to get a physical intuition, this is what is happening. So it's like there are some certain holographic states in black hole, and so this is how much it takes, how much emission, let's say, or whatever it takes you to take from one holographic state to the other. Okay. Now again, as I said, I don't see big fundamental so far. Maybe tomorrow I'll see something else. I don't see at the moment big fundamental meaning of this expression of y 60 minus whatever. It's just some dimension dependent. And so what is important is not this precise expression. The important thing is that there is a macroscopic variation of n. Okay, relatively macroscopic. Of course, it's much smaller than n. Okay, delta n is much smaller than n for sure. But still, it changes the macro state. Okay, it's much larger than 1, and so it takes you from one micro state to the other. Now, the spectra behave differently. What happens? We have decreased the n. Correspondingly, you see what happens, right? Since we decrease the n, this term is less important. Okay, so therefore, the momenta, the spectrum, follows free spectrum for longer time before it sees the interaction. That makes sense. Okay, so we have to follow spectrum for a longer time. And so then it comes down here again, right? So these are gapless modes, state this one, and this is this one. And they correspond to one holographic neighborhood and another holographic neighborhood. Now, you see what is important. The important is that in between, there is nobody gapless. In other words, if I change n, not by delta n, but let's say by delta n minus 1, by delta n over 2, okay? There is a state in between which never touches 0. This is the point. Okay, do you have color chalk actually? Then let me. Actually, let me plot in different colors. So this is okay. Then we have beautiful. And even blue, we have even blue. And then like that, okay? So this is n minus delta n over 2, let's say. This is n minus delta n, this is n. And this is the free spectrum. Now, so therefore you see what happens in between. In between, what happens is that there is, the state never touches 0. So there is a terrain where you have to abandon holography, go through, and then you reach another holographic state. So this is somewhere in between here. This is the state somewhere here. Okay, so now we have a full picture. Yeah. Exactly. We are going to discuss that. Yeah. So of course this works as long as n is large. So when with decreasing n, as you said absolutely correctly, with decreasing n, the story mixes up. In other words, of course, if n is 0, as I said, you simply don't have any holographic state anymore. Nobody, right? And this illustrates the point because with n0, you have to go farther and farther. And the modes follow free spectrum higher and higher, okay? Therefore, in any sensible theory in which you have certain maximum momentum that you can reach in your experiment or whatever, okay, you eventually have to abandon holography because there will be certain maximum. For instance, in gravity, this will be Planck scale, okay? So it will be, okay, and so on, right? Any other questions? Yeah. No, delta n, so okay, excellent question, right? I was going to comment on that. Now, Here I'm requiring that it's integer. So I'm setting from the beginning, of course, I'm setting lambda, e over lambda in such a way that these delta m's are integers. Now, strictly speaking, they don't have to be exactly integer. What you need, they have to be sufficiently close to integer, because obviously, I mean, once we take into account, we also said this yesterday, once we take into account the effects of interactions, of course, for any finite n, this gaplessness is lifted by 1 over n effects. So yeah, so the rule of the game is that as long as you go to sufficiently close up to 1 over n effects, that's what I'm discussing. So yes, you can do it strictly integer, but that would be completely artificial. That would be only true in a free theory, in which the Hamiltonian is just this, and I completely ignore interaction terms. Okay, so which corresponds to precisely this double scaling limit that I gave. Okay, but yeah, otherwise absolutely. But also the n, we should understand that n is an expectation value. An expectation value doesn't have to be an integer, right? So for instance, if you consider a coherent state of A0s instead, it doesn't have to be integer, it could change. So, exactly. So here we're talking about the, so you can, in this discussion, you can think of it as being a continuous variable, okay? But even if it's a continuous variable, of course, the jump, k must be an integer. That's the point. And since k is changing, right, there is a finite jump that n has to experience, okay? Anything else? All right, very good. So now we have this picture. Very nice. And now the question that we asked was, let me see if I have to say anything else at the moment. No, nothing else. And now the picture was, the question was, very nice. So we see that we are recovering some black hole properties. We are recovering property of holography. We see that there is an area low entropy. We see that there are states separated by certain terrain, which are holographic. We can store information. Okay. Now the question is, what about decay? If I allow the system to decay, what happens? Whether all other properties of black holes are also reproduced, okay, in this discussion. Now, to allow the system to decay, we have to couple it to some external reservoir, right? So in the case of black holes, this is free particles, right? So in a spectrum, if I think of a spectrum around black hole state, I have certain excitations, mysterious excitations of black holes. These are precisely the ones that we are trying to demystify and uncover. And a free spectrum, continuum, right? And this the evaporation, Hawking evaporation, is a transition from black hole spectrum to continuum. So there is some transition which allows modes from black hole spectrum to go into continuum spectrum. Okay? This is completely independent from what is your microscopic theory of a black hole, because that's what should happen according to rules of quantum field theory, right? So therefore, in order to understand what happens, we should introduce a prototype for this external reservoir and couple the system to that prototype. Okay? And so let me write there. So the prototype for me would be very simple. I will introduce another set of modes. Let me call them chi. So psi was expanded in spherical harmonics, right, on a sphere, right? So there will be similar story with chi's. So I'm introducing a chi sector theory. And all I need to do is to allow particle conversion of modes from the sector psi into the sector chi. Okay? You can choose whatever you want. In principle, it looks like, okay, it looks like that the the answer, the qualitative feature that I'm after, is not sensitive to this. Okay, so therefore we can take a simplest conversion of psi's into chi's. So we add to these Hamiltonian terms that are, okay, so chi has its own kinetic term, obviously. And what is chi mixes with psi. So there is a mixing. Let me call this parameter psi for a moment. We'll constrain it in a second. Mix. Let me parameterize it as 1 plus Laplacian. Okay. Now, you can add arbitrary number of self-interaction terms for chi, etc., etc. But what we need to do, we have to respect the rule of the game. What is the rule of the game? What I'm trying to understand is this. I have a sector that is holographic. And I'm coupling this sector to an external sector, external reservoir, which is not holographic. These are outgoing quanta, the prototypes of outgoing quanta of Hawking radiation. So therefore, their dispersion relation, their own dispersion relation, if I exclude mixing between these two sectors, dispersion relation of chi's essentially is the same as dispersion relation of free particles. Okay, so now these are dispersion relations also of chi quanta, because chi quanta they don't have criticality, they don't have holography, they are not holographic. Okay. Now, so therefore this is also dispersion relation. This thing, this line, is dispersion relation also of chi quanta of B of k's. Okay. Very good. So now this is our Hamiltonian. Okay, so now what are the constraints on psi? We'll constrain psi in a second. Okay. Let me move the blackboard up. Yeah. So we have to constrain the chi sector. Sorry, the psi, the mixing. Now, the only condition I will impose on this mixing is the obvious one, that interaction between these two sectors is not upsetting the holography of the holographic sector, which is of course true for a black hole. The fact that black hole interacts with outgoing radiation is not changing the entropy of is not destroying completely entropy of a black hole. It's changing it a little bit. So in other words, of course, we cannot avoid that there is an offset, but offset should be mild. Okay. So now, in order to quantify this, let's see what happens, right? So in this limit. Let's see, this Hamiltonian, actually, sorry, yeah, I can write right there for a moment. Sorry. I have to bring it all the way down now. So the Hamiltonian here will acquire additional terms, right? You know, not to keep rewriting this all the time. So there will be additional terms. What will be the additional terms? Will be sum over k's, same exactly sum over k's over b's, right? Okay, and mixing between A's and B's. So the mixing between A's and B's is psi mixes 0 modes. Yeah, sorry, instead of 1, let me parameterize the. Because since this system has dimensionality of energy, as you know, so it's E, so therefore there is mixing psi E, and then there is mixing with the other sector, which for large case I can ignore 1 there because delta, as you know, right, delta is E times delta of theta, right? Theta is the angular rescale, and so so this will be the following. It will have the following form: psi E times omega k A0 AK dagger BK plus Hermitian conjugate. Okay, this will be the part of the story, and on top of that there will be interaction terms. Interaction terms among the K modes. Okay. Now these interaction terms that do not enjoy the background, they are suppressed. They are suppressed by powers of 1 over n. So these interaction terms will have form, for instance, E over lambda, omega k prime, and sum over coefficients, C alpha, beta, gamma, delta. These are simply coming from the integrating over spherical harmonics and transitions between different modes. All these levels, they all belong to K star and K star prime, because those are the ones that are we interested in, and so on. Okay, so interaction terms. So these are interaction terms. Okay, now I think I can move the blackboard up. Now let's ignore for a moment these interaction terms. Let's focus on this Lagrangian. Oh, sorry, Hamiltonian. Again, don't get confused. Here I ignore the 1 because omega k's are very large. They are much larger than 1, so therefore 1 is irrelevant for this discussion. Yeah. Now, what is the story? So the story is the following, right? So now, if I concentrate on this Hamiltonian, which is bilinear in A case and B's, this Hamiltonian splits very nicely in 2 by 2 Hamiltonians. Okay? Why? Because of momentum conservation. So each harmonic is projected on its counterpart. Okay? So therefore, there is a Hamiltonian of bilinears has the form AK dagger and what do we have here? So here we have epsilon k coming from the diagonal part, from this part, and the mixing term psi E omega k, psi E omega k, and here we have a diagonal term, which is E omega k. Okay? So for each k, Hamiltonian is simply sum of 2 by 2 for all the k's. Now, who is epsilon k? Epsilon k's are simply these guys, this spectra, right? So which come from there. So epsilon k's are omega k, 1 minus, and E over lambda, omega k, n squared, right? Okay? So now we have the following situation, right? So the situation is, if I demand the exact couplessness, right? So this part, therefore this will be 0, right? This will be 0 for exact couplessness, right? For n that satisfies this condition. So then I would have 0. And now the question is, because of the mixing with the non-holographic sector, of course this 0 will get offset. And in order not to destroy holography, this effect should not be more important than something. Now, that something is up to you, okay? The reasonable something is, for example, again, this is an example. You can demand other measure, but for example, I would say that it's reasonable to say that the effect of offsetting, the effect of mixing with the outgoing radiation, okay, should not be more important than changing n by 1, okay? Delta n by 1. So there should be some kind of 1 over n effect, okay? Let's see what happens. If this is what we demand, what happens? If I change delta n by 1, right, how does epsilon change? So what happens with epsilon? Right, epsilon will change as u omega k, right? And then here we have 1 minus omega k n, right? And let's write it for generic delta n first, okay? So it will be minus e over lambda omega k delta n square, right? Now, this is 0. And so the change would be given by, so now this is 0, and therefore this is 1 over n. And therefore change will be e omega k delta n square over n square, okay? So generically, this change will be of that form. So now, if I'm demanding that the effect of this mixing between the sectors should not be more stronger than delta n equals something, that something is up to you. Let's, just to be clear, let's take delta n equals 1, not the effect. Then I would say that then you can see very easily that this would put here the following matrix. Right? So this would put here the following matrix. Very nice matrix, actually. Okay, so it would be 1 here, xi here. Here we would have delta n over n square, which would be, if for 1 would be 1 over n square. And e omega k will factor out. And this will tell you that psi should be less than 1 over n. Okay? Again, I'm not insisting that if you want to play around with this type of models, you don't have to take 1 over n. You can demand milder condition and see what happens. Okay? I'm just saying 1 over n, it's one of the choices, which is, of course, absolutely reasonable. Because it's not offsetting anything about holography. Okay? Very good. So now, with this, now we have fixed psi. And therefore, Hamiltonian, this Hamiltonian for k mods has a very clear form. Now it will have here one, so, right? So now, once I plug this information here, and I consider generic delta n, okay? So delta n equals 1 was only to restrict psi. But after I restrict psi, I should allow delta n to be whatever, because now I'm looking for the evolution of the system, okay? So therefore, this mixing matrix between the modes will be simply omega k. Here we'll have delta n over n square, 1 over n, 1 over n. Let me put factor of 2 just for convenience, and 1. Okay? This is the mixing between k mods, between AK dagger, AK, BK dagger. Now, the difference for zeros, there will be also expression for zeros. So A0, of course, doesn't have anything here. So for A0 and B0, there will be only off-diagonal mixing. Zero, 1 over n, 1 over n, 0. Okay? Now, let's see what is the evolution of the system in this case. Okay? in general, right? So this it simplifies the problem enormously, captures all the essentials of the story, simplifies it enormously. Because of momentum conservation, since it splits to 2 by 2 sectors, 2 by 2 sectors. Now, let me remind you the generic formula, right? So if I give you mixing between the two Hamiltonian that gives you 2 by 2 mixing, okay? Of this type. Let's say I have Hamiltonian, some A's and some B's, generic. Okay? So I have some A here, some B over 2 here, B over 2 here, and some C here. Okay, some generic Hamiltonian like that. And I want to do time evolution of this Hamiltonian, okay? Starting from a state, let's say, in which at the beginning only A is occupied and B is in the vacuum. Okay, so I start with initial state, t equals 0, with the state for this Hamiltonian, where A is occupied to a certain number, Na, Na of A, times, and B is in the vacuum. Okay? And I time evolve, so this is the Hamiltonian. This is the Hamiltonian, and I time evolve the state. There is an exact time evolution of the state by time evolution operator. Okay? And now, so the state evolves in time, and now if I ask, what happened? Very dramatic, this place. So now the state evolves, and I ask the following question. So at the beginning, the expectation value, occupation number of A was Na, B was 0, and how does they evolve? How the occupation number leaks from A to B, okay? And there's a simple expression, right? So expectation value of A changes as initial value, okay, 1 minus, and the object, which is B square, A minus C square, plus B square, and sine square of certain T times delta over 2 H bar, where delta is simply square root from this guy. Okay? And correspondingly, the expectation value of B changes as Na. The same thing. Of course, the evolution is number conserving, so the total number is conserved, and so we have this, right? Okay, so now this means the following. This means that so now let's apply this to our story there, right? So our story there was that we were in the state K star, and in the state K star we had a pattern, information. So information pattern was encoded in the modes of K star level, right? So so we are starting from an initial state in which we were in the macro state. So our initial state is a macro state in which A0 is occupied to n, certain n. Okay, this is A0. B0 is in the vacuum. Now, K modes, K star modes, are in certain pattern. I have encoded information in K modes. Okay, so I have N1, ta ta ta, n, figure n, k star of k star. Okay? Who else of the k star modes of sector A, right? So let me call them A k star modes. Right? Who else is relevant? So the relevant people are similar things in the B sector, outgoing radiation that has a chance to copy the information. Okay? So the similar guys in B sector. In B sector, they are in the vacuum. So B of k star is in the vacuum. Then, who else is there? And the next holographic level, which is also in the vacuum. So N, so here, next holographic level, A of k star prime is also in the vacuum. Okay? So this is the initial state. And everybody else is in the vacuum. Okay? So macro state parameter N, right? And a pattern. And now we time evolve this story, okay, and see what happens. Now, the following processes take place, right? Momentum is conserved, so angular momentum, everything. So A0 goes to B0 according to that law, and each AK star goes into BK star according to the same law, okay? Then on top of that, there will be a process due to the interaction terms, which I have ignored. And the interaction terms, they can give you transitions between K stars and K star primes and everybody else, okay? Right? Let's, for a moment, put aside the interaction terms and see what happens. If there were no interaction, what would happen, okay? No interaction among the holographic modes. Of course, there is an interaction between the sectors, right? So then we see that A and B oscillate into each other. But before we discuss A and B, so let's assume for a moment, not oscillate, they leak, right? So somehow let's think in the following way. Okay, let's assume for a moment that A0 goes to B0. Right? Because we want to understand first how the decay proceeds, but we also want to understand the effect of the decay on the information. Okay? So let's first assume, we come back to this immediately, assume that A0 goes to B0, which means that A0 is losing particles. Okay? So we are losing particles to outgoing Hawking radiation. Okay? Now, in the same time, let's see whether we have a chance to encode some information into this outgoing Hawking radiation, okay? Now, this chance at this level is only realized by this 2x2 matrix, this thing, okay? This is the only source of this, why? Because momentum is conserved, so which means that the pattern should be copied into analogous pattern or in some unitary transform into a B sector of K modes. Right? So, very nice. Then we see what will happen. We know now that question, right? So now if I have a pattern that is N1, Nk star of AK star, does this pattern have a chance to be encoded into the similar modes of Bs? In other words, can I encode it into something, some N1, so these are N's of A's, right? Can I encode them into some N1s of B's, N2s of B's, N, Nk stars of B's, of B, K star? Question is, can I do that? Well, the answer is here. Let's see. This is the evolution for each NA of B. Okay, this is how they evolve. So each NA of B, well, here is the NA of B, right? So this means that N corresponding Nj of B evolves in the following way. Same Nj of A times this object, where B's, A's, and C's are fished out from this matrix here. Okay? So let's see. So B is 1 over n. Okay? So we have 1 over n, and in front is e omega k, right? So we have e omega k square, right, times 1 over n square, and then times 1 over, so 1 minus, right, so 1 minus delta n over n squared minus b squared, right? Sorry, plus b squared. So 1 over n squared. Okay. So this is the picture. Times sine square of t times delta over 2. Okay. Now this, I come back to this in a moment. So this tells me what is the amplitude, okay, by which B has a chance to change, by which B changes, okay, in this system. So let's estimate this amplitude. So sorry, and then this, of course, the whole thing is multiplied by e omega k, and this cancels out. Omega k squared cancels out. So the form is simple. Therefore, we get Nj of A, Nj of B, sorry, goes into Nj of A, and the following structure, right? So 1 n minus delta n square over n squared plus 1 plus the time-dependent part. Okay, so now, what are we learning from here? Well, we are learning from here something very important, that the information transfer is enormously suppressed, but it's not zero. Okay, so despite the fact that the pattern is essentially maintained within the system, within a black hole or whatever, still there are glimpses of this pattern encoded in outgoing radiation with extremely suppressed amplitude. Now, how suppressed is the amplitude? Now, unless delta n, so now let's stare at this expression, because this expression is extremely important. And I need some space. Let's see, what can I sacrifice? Okay, let me see. This one. So first, we see the following thing, right? We see that now this delta is given by this expression, right? So delta is large. So there is no issue in time suppression. So what happens is that delta is large, so the sign jiggles, okay? So there's a jiggling. What is important is the amplitude, okay? The amplitude behaves in this way, okay? So, which means that the copy of so this means that effectively you are generating a copy of the pattern, okay, with this suppression, okay? Now let's see, let's analyze this suppression. Okay, so this is the expression. Now for delta n equals 1, let's say 1 Hawking emission, or 1 quantum emission. Okay, to map it on Hawking emission is a bit tricky because of course we are not in a black hole, but there is some emission, elementary emission. Okay? And for that emission, the pattern from A is copied on a pattern from B, but with an amplitude which is suppressed by 1 over n squared. Because you can see that for delta n 1, this suppression is enormous. However, it's not zero. So there is a pattern translation. And so an external observer, if this external observer has an enormously powerful microscope, could resolve this pattern. But of course it will take very long time. This is one thing, okay? Second thing is that for delta n large, when black hole finally evaporates, there is a full translation, right? So because then there is no suppression anymore. So this tells you that sooner or later, this pattern, of course, will be released, okay, into an outgoing system, okay? The system can read it. But these are two separate stories. In other words, you see, there are two separate effects. We should understand that pattern is always a little bit available for an outside observer. There is a correction to Hawking evaporation, which is not surprising. I will come back to it. That's obvious. That must be the case, right? But so you see that there is a correction to Hawking evaporation, and the pattern is always a little bit accessible to an outside observer. But it's so much suppressed that this observer should collect a very powerful microscope and start resolving it. And so now we see what is the picture. So the picture is, let's say I'm an outside observer. I belong to sector chi, and you are an observer that is powerful enough to understand everything about black hole. Okay? And so your quanta, psi quanta, have a pattern, and I'm trying maximally hard to see this pattern in outgoing radiation. I see that it's extremely suppressed. So I need an extremely powerful microscope, but that's not enough. I need a lot of time to observe this suppression. So I'm staring at the pattern, okay, for a very long time. Meanwhile, you continue to send me particles. Meanwhile, your delta n increases. And with increase of delta n, you release bigger and bigger portion of pattern into outgoing radiation. So I have a double help. I have a help that I have time, and I'm staring at the pattern that I got, and this requires time to resolve it. But also, I'm getting more and more enhanced signals. Finally, there is a situation when the two meet, because on one hand, I had long enough time to stare at the pattern, and now I can say, oh, I see really what is written there. And on the other hand, the pattern becomes unbearable. The memory burden becomes unbearable for a black hole. It has to release it, okay? So let's try to understand it in this level of that diagram, the above diagram, okay?
What's the time scale you need to actually see something?
Well, as I said, you see, the thing is, my intention, of course, wasn't to reproduce black hole timescales. But it's really astonishing how well this reproduces black hole timescales. If we normalize to certain, we have to normalize to something, right? Let's say 1 emission time or something. So I would not expect the timescales. So for me, it would be absolutely satisfactory if I learn that the information release is non-zero and the timescale of release is macroscopic. That would be, for me, absolutely enough to complete this checklist that I gave you. That this would mean that this system behaves essentially like a black hole. Quantitatively, there may be differences. But I'm really surprised how close really the scalings are. So essentially, if we include all these interactions, etc., which I didn't include, it looks like you are really reproducing pages time. What would be pages time for this system? Okay, so pages time, let me remind you, it's the time scale on which, with very general arguments, you can conclude that this is the required time scale for an outside observer to start resolving the information that comes out, okay, at order 1 rate. And okay, this reproduces that. So it looks like that even that property is universal in systems with enhanced memory capacity. What this means, I don't know. I don't know. For me, it's a surprise because why it should be exactly the same quantitative scaling, I don't know. But it is, okay? But okay, anyway, so at this point, I'm after qualitative features. Yeah.
But doesn't it depend on your choice of psi, essentially?
That's the crazy part. That it seems it does not. It seems that whenever I force psi to be holographic, whenever I have this property, it looks like that everything comes from these holographic features. And it looks like that these holographic features are very robust and they are system independent. It's sort of, probably this has something to do with what Dieter was asking, with conformality or something like that, okay? Now, I don't know why, okay? I don't know why of course I didn't check infinite number of models, that's true. So it could be that it's just an artifact of some coincidence. In any case, I mean, the second part I don't want to insist on. I'm not insisting that all these theories should have quantitatively same behavior same scaling as this has to be investigated. I'm fully satisfied with qualitative behavior, okay? Yeah.
Are you saying that holographic systems always have Hawking radiation?
No, every system has radiation. I mean, systems normally decay.
It's a special Hawking radiation.
No, I'm saying that if you have a holographic system and you allow this holographic system to decay into an exterior system, some external reservoir, in some way, it seems doesn't matter, and if you satisfy the condition. So here's what I see. I see that if I require from this external reservoir that this external reservoir is soft enough in order not to offset the holography, then this thing follows. Of course, you can always have external system which just destroys your holography and that's it. I mean, that you can obviously. But again, I'm not saying that I have a theorem or anything like that. This is what we are observing. This is an observation. Okay. Yeah.
So you're not disagreeing with this basic curve, what is sometimes been called the page curve that goes up
and entanglement. No, of course no. No. So I'm trying to get there, but I'm not yet there. So.
But that you think that comes out?
Absolutely, yes, absolutely, yeah.
That sort of makes sense because.
Yeah, that makes sense, but absolutely. But in certain sense, you see, it turns out that this curve actually is even more generic than holography because we checked this curve for a system which is actually non-holographic, one dimension. So it has gapless modes, but it doesn't have area scaling. And my students, my collaborators, Alex Pretzel, Nico Wintergest, and Daniel Flassig that were here, and Cesar Gomez, of course. So we were analyzing first that type of system. It was not holographic. But despite the fact, it seems that this is sort of even more universal than holography. In certain sense, yeah. So that's, yeah.
Well, paid sort of reason to that curve based on.
Yeah, he didn't include holography. I mean, absolutely, yeah.
But then, so what is it about this model that really makes this black hole-like? It's simply this large capacity?
Yeah, that's right. So in other words,
Anything more than that?
no, it seems nothing. It seems that, so that's the surprising part. In other words, what I'm observing, again, I don't want to mislead anyone to say that I have a theorem or anything like that. I don't have a theorem, but it looks like what we are observing, okay, that every time there is I ask from a system that it has enhanced memory capacity, in my definition, the one that I gave, it's out, and if system is rotational invariant, it automatically satisfies all these properties. Now, of course, you can say that why should I insist on my way, or my definition of capacity of information storage? Maybe there is some other way in which you can store information. Of course, that's a separate question. that I cannot insist it. But there is this absolutely surprising and striking observation that the moment I insist on that, all these qualitative features of black holes, they come out. Okay, so that's.
But for example, this could be a model of a star with a large information.
No, the star doesn't have it because it's not holographic. That's the problem, because you see, you need some kind of criticality in the system.
Okay.
No, for star, this will not work actually.
Well, for example, it's not clear that, say, an observer traveling through this would, observe what we would predict for traveling through a black hole spacetime.
No, of course. This is a look. I mean, again. So let me explain this. No, absolutely. I'm. So.
At some point, you're going to change it in. Well, you're going to build these out of gravity.
Of course, yes. So the questions about space-time, exactly. So.
It doesn't really look like a black hole for me. Check.
Yeah, I'll tell you. Yeah, I'll explain in a second. Let me just move this up. Sorry, it's very slow. Okay, so now, in other words, again, so not to keep repeating myself. So the thing is that, for instance, a star-like object or some other system that's not holographic would have a spectrum something like this, some spectrum like that. Okay. So in other words, what makes the system, in my definition, holographic is that when the system is touching zero. In other words, for instance, for star is something like this or something like that, whatever, right? So therefore, it is crucial that you have interaction with negative energy, attractive interaction, among the modes. And it's crucial that there is a regime where this interaction is important. So this is what I'm observing. The rest follows. Now, of course, there is a question now. So the whole discussion is about information properties, right? Obviously, I'm not saying that this object is a black hole or anything like it has a horizon or you're going to fall in it and whatever, right? Because this is an object which we can reproduce in laboratory even. If you have cold atoms, let's say, in fact, I'm trying to convince our colleagues to do something like that. So if you have cold atoms, these people with cold atoms, they do extremely sophisticated, extremely interesting. They can manufacture all possible interactions. So this looks like a system which, in principle, okay, you could manufacture in laboratory. Of course, it's not a black hole with a horizon or anything like that. So in other words, here we're covering the information aspect of the story. Okay. Now, of course, once I go to a black hole, probably next lecture, I will try to manufacture the same thing with gravitons. So of course, I will replace size with gravitons. That's a much more ambitious program because there I also want to reproduce properties such as geometry, horizon, and other properties of a black hole. But this gives you a guideline because this gives me a guideline. This tells me that, look, if you want to understand microscopic theory of a black hole. By the way, I'm not saying, so first of all, I want to make it very clear that when we are trying to understand phenomena of nature, there is always more than one language to do that. You should not think that I'm telling you that this is the only language in which you can understand black holes, and you should not think about quantum gravity, different approaches to quantum gravity or duality or whatever. Absolutely not. I'm saying that there is an A language which for me is extremely physical for someone like a particle physicist, because we think in terms of particles, their interactions, their states, etc. And so this language is telling me that if I want to translate this, if I want to use dictionary, and this gives me a guideline where I should look. What kind of system should I look in gravity? This tells me, okay, look to the states which high occupation number of gravitons, okay? Because they have all the ingredients for this type of behavior. So in other words, Now, there is a huge evidence from gravity side of the story, which I will discuss separately, that this is a correct picture of a black hole. This is a correct A language to describe a black hole as a multi-graviton state, okay? But that's a separate story. I'm saying, even if you don't care about black holes, you don't care about gravity, but you only care understanding most fundamental aspects of information processing. This is the observation that we see, okay? So it looks like that the systems with enhanced memory capacity, they act universally, in certain sense. And this is fascinating, because I don't know, maybe our brains act like that, or for sure you can build artificial brains based on this, because, I mean, artificial brains are just like physical systems, right? So you can build artificial systems, artificial intelligence, which stores information in this way, because this is about storage and energetics. This is not about algorithms. You can take this and then play around with algorithms. Okay. Now to come back to Steve's question and to continue this other discussion. Now we see what is happening. So what is happening is that. Let me write it like this. I don't know what's going on. I know, yes. So here we have a pattern which is stored, right, in these modes. So these modes, they are like a cheap tape that you can have, right? So you can have a very high quality tape sometimes, not very often, which is cheap, right? So these of this type. Now, there is another tape which is made out of B modes of the same momenta. Now, of course, this tape is extremely expensive because this is enormous energy. So this tape here, okay, this is an expensive tape. Now what happens? Now you understand the picture. So what happens is that when black hole evaporates, cheap tape does two things. First, it tries to rewrite information on an expensive tape, on here. But because expensive tape is very expensive, the information, the amount, the amplitude in which you can rewrite information is extremely suppressed. It's suppressed by macroscopic scale. Okay? Now, this is one thing. Meanwhile, black hole evaporates, okay, or the system evaporates, the system, and your tape that was cheap becomes expensive. Why? Because you are climbing up this ladder, okay? So you are deforming this curve from here to here. So the tape that you had that was cheap now becomes expensive. Now it becomes not so expensive as the corresponding tape, outgoing tape, okay? But becomes more expensive than it was. Now, what the system will do? Okay, let's make a guess. Of course, what it will do is, at some point, it will try to rewrite the message from the original chip tape to another chip tape, because another chip tape is another holographic state. Okay, so there is another chip tape, and so that's obvious. This is exact. So the system is doing exactly what you would do. Right? If you have a nice music at home and you want to, and your disc or whatever wears out, okay, you will not run and buy expensive tape immediately. If you have another cheap tape, you will wait a little bit, try to survive, and then rewrite it on a cheap tape, right? And this will continue until the cheap tapes become as expensive as the expensive tapes. And this happens precisely as we saw, incredibly, we see that this happens precisely when delta n is order n. So once you make delta n order n, you have exhausted all your cheap tapes, and so they are no longer cheap. So they become as expensive as the tapes that you had that are outside. And at that point, of course, there is no obstacle to completely release information. But as I said, it's extremely important that parts of the information you are still copying on an expensive tape. You're only copying on an expensive tape with an extremely suppressed amplitude. Okay? So it's as if you are sort of, I don't know what compare this in life, but it's like there is an expensive tape and you hack in it or do something and, okay, try to store a little bit your pattern. Anyway, so this is what's happening, okay? So this is this constant. So therefore, to summarize, there is a constant rewriting of the information internally going on. And by the way, do I have 1 minute? What is? Can I show? How much time do I have? I finished, right?
Yes,
yeah. Yeah, I can show a graph because this was done by.
shall I turn on the?
Yeah, that would be great. Yeah. Because this is okay. There is nothing surprising in this graph, but it's like it's numerical analysis, which. Yeah. I think time, sorry. Yeah, so meanwhile, basically the graph will show precisely what I said, but numerically. It was done by guys here, and you can see. Okay, here by these people. Now this graph shows numerical analysis of this system, literally what I discussed. Okay, and you can see that if you don't allow the rewriting of a pattern among chip tapes, so the first graph is the situation when interaction among different holographic modes is switched off, which means the pattern is just stored forever in one of the holographic modes. The leakage of the pattern is extremely suppressed, and as you can see, the whole system is wiggling around the constant situation. So there is a pattern. So they're not. I don't have a pointer, but anyway, it's obvious. So there is A0, B0, and K sectors. Okay, and right. Okay, so the K sectors, and so you see A0 stays essentially constant, occupy all the B0 constant, and so the patterns are not exchanged. And here, once you have interactions, you see what happens, that the pattern gets rewritten from A, the green is like a K prime, and black is K. So you see A evolves, so A leaks to B, so A goes down. B, which is a red line, goes up. Okay, there is evaporation. So this is literally Hawking evaporation, counterpart of Hawking evaporation in this toy system. Okay, so this goes out. And then the pattern gets rewritten from the level K star to level K prime. Okay, so from one chip tape to another chip tape. Okay, so let me finish here. And so, okay, take questions, of course, if you have any. Yeah. How can there be an information paradox? The whole lecture I'm talking about is a unitary system, right? I mean, how can there be information? How can there be a paradox in physics? I mean, tell me. Paradox usually means that we don't understand something. Now, my whole lectures are trying to understand something. Okay, and you are asking me about information paradox after 3 hours of my discussion that it's not there. No, paradox, when physicists say paradox, this simply means, paradoxes are fun, because paradoxes are, in physics, paradoxes are always seeming paradoxes. What we call paradox is that sometimes we don't understand something, and that's why we think there is a paradox. Now, in a microscopic theory, which is unitary, there cannot be a paradox, because it's a unitary theory. Now, what you can blame on microscopic theory is that there's not a theory of nature. That's of course true. You know, you can tell me that this model has nothing to do with black holes. Then no problem. That I don't have a proof that this is a theory of a black hole. That's for sure. But what I can guarantee, for sure, and that's obvious, I think that's obvious, that in this model, despite the fact that this does everything that black hole does qualitatively, of course there is no paradox because it's a fully unitary system. Okay, so that's what I can do. I can only build, you see, we can only build models of nature, okay, and show that those models work. That's the only thing I can do. And then you should decide whether this model is convincing enough to think that it's a theory of gravity, or it's a different theory, which is not a theory of gravity, which behaves gravity-like, which is also interesting. I think it's absolutely cool if our brain, let's say, shares some properties from black holes, but of course, obviously, it's not a black hole. That's for sure. Yeah.
So, but really, whether you want to call it a paradox or terminal crisis or what, the essential point is how can you have something that looks like a black hole and behaves for many purposes like a black hole, but still has unitary evolution? That's really the question.
Yeah, that's what I'm trying to answer.
Well, okay, but an important step in that is the first step of getting something that looks like a black hole and behaves very much like it for many purposes.
Yeah.
So, this is, it's certainly worth trying to think of models with certain properties of black holes, but you really have to get there to see whether, how you're addressing the paradox.
No, sure. In other words, okay, absolutely, yeah. I mean, I agree with that. I just said the following, that my approach is to go from many different directions. Okay, so now, on one hand, Cesar Gomez and I, and we were developing for several years a theory of a black hole being a multi-graviton state, and we have huge evidence that whenever we can compute something, it works. Okay, and also it predicts things. It predicts things, by the way, that were also predicted later by other approaches. So other approaches, for instance, I don't know, for instance, this fact that after macroscopic time, entanglement should set in and stuff like this, these were predicted by our theory before, and so other theories predicted, which is great. So the other approaches also, so in a sense, it's not a disconnected, world. It predicts certain things that are reasonable. That's one approach. Okay, so that is one thing. Now, unfortunately, the gravity framework is not powerful enough computationally. We can compute certain things, like Dieter, Cesar, and Stieberger, and us, we computed, for instance, graviton scattering amplitudes, 2 gravitons into many, and in the regime in which this computation was under full control, we found an astonishing fact that this indeed reproduces a black hole entropy suppression. We did computation both in string theory and in quantum field theory, and both computations agree in large N limit. We showed this explicitly. Then this same computation was repeated by Veneziano's group, Veneziano, Andazzi, Bianchi. So there is this computation of scattering of 2 gravitons into N, fully fledged quantum gravity theory computation in the regime where you can control it, and we see, indeed, this captures black hole entropy. Again, of course, we can always say that it's a coincidence. No, that's a fact. You can go and check out. I mean, there is no question that it reproduces exponential suppression with black hole entropy in that regime where you expect the quanta to have softness of the radius. And
the regime where you actually do something like making a black hole at high energy.
no, I'm not saying it's making a black hole. I'm saying a very concrete thing. I'm saying the computation of graviton scattering amplitude 2 to n, fully fledged quantum gravity computation in large N, shows that when the softness of outgoing gravitons is given by certain number that would reproduce Schwarzschild radius, okay, in the same time, the suppression factor reproduces entropy. We see this correlation. Now, this correlation is highly non-trivial. Also, it's non-trivial that Feynman diagrams, resummed to infinity, capture quantum gravity effects, non-perturbative quantum gravity effects. To me, sounds non-trivial. Now, of course, we can always say that things are coincidence to infinitum. We can always say, oh, this is a coincidence, No, my point is the following. From quantum gravity side, I am gathering evidence where I can. Because I claim that the black hole description as multi-soft graviton description at the critical point is a valid description. I'm not saying this is the only one viable. but it's an A-valid description and should be taken seriously. This is one thing from the quantum gravity that I will discuss in the next lecture. At the same time, I'm taking a different approach. I'm saying, look, let me understand whether information processing properties are universal and not necessarily bound to black holes. And I'm discovering, and that's a fact, that information processing properties that we thought were exclusively gravitational and black hole type, at least I thought always, I see that these are explicitly realized in the systems which we can even solve, sometimes exactly. That's another fact. Now, the point would be to put all these facts together at the end of the day, and then see what we'll decide. Maybe we'll decide that something useful we can learn from here, but it's not a theory of gravity. We can learn from somewhere else. And again, I want to be crystal clear that this doesn't mean that this is the only approach. Of course, there are absolutely valid approaches, different questions, you know very well. We can ask many different questions. We can approach the story from many different sides. And most likely, the reasonable approaches are all correct. There are different ways to understand same phenomena. I don't have any issue with anything, but I mean, I have to defend the things that I see. I cannot say that these things are, they don't matter. I think it matters. I think these coincidences are very important and should be taken seriously, but of course it's a question of taste. I mean, you said yourself that we agree that unitarity cannot be violated. That goes without saying. In any case, I mean, you can take it as my assumption. My assumption is that unitarity should not be violated. We should not sacrifice CPT invariance, causality, this kind of stuff. So I'm working within that framework. I don't want to discourage anyone to go beyond that, of course. Maybe there is a reasonable theory. Look, we may be all confused.Maybe there is a reasonable theory in which somehow, I don't know, causality can be violated a little bit. I don't know, but I don't think so. That's the only thing I'm saying from the experience. But anyway, but of course, these kind of questions are extremely important. I fully agree with that, what you are saying. Yeah.
Okay. I think in
Yeah.
time we should probably postpone further.
Yeah.